I'm Andrew Larkins from Sygensis. I'm the CEO of the business, and today we're going to talk about a project called Resilient Electric Vehicle Charging, or REV. And just to let you know that this session is being recorded and will be available afterwards on YouTube. And if you have any questions, please do drop them in the Q&A or in the chat. So there have been a vast number of projects about EV charging in the past, undertaken by all sorts of different organisations for all sorts of different reasons. The thing that makes this project different is the fact that we are talking about more than just providing the energy to charge cars, more than just providing the kilowatt hours. The specific area of interest is looking at what happens in fault conditions. So what happens in the first few seconds after a fault, be that a failure within the power system, the typical flicker of the lights, or given that we are talking about smart charging and vehicle to grid, the risks of failures within communication and control systems for that smart charging. So Project REV is looking at the impact of electric vehicle charging on short-term frequency, voltage stability, and cascade fault prevention and recovery. The session today covers the project which has been undertaken for National Grid ESO, and it was funded through the Network Innovation Allowance. One of the great things about this scheme is that the key findings are made public, and you can find the 2 reports that we have produced from this project on our website. We will share the slides with all participants after the event, along with a link to the recording. So this webinar is a recap of the Work Package 1 activity, which was a general introduction to the subject area and identification of some of the risks. Within Work Package 2, we're going to cover that in 2 slides as a quick introduction, and then delve into detail of a few specific areas which we found particularly of interest. What I would, however, highlight to everybody that the 2 reports, Work Package 1 and Work Package 2, do cover different topics and different levels of detail. Don't rely on Work Package 2 to provide all the answers. And within this webinar, we will emphasise some of the recommendations we've made, and at the end, we will be taking questions. And presenting today will be myself, Andrew Larkins, the CEO of Sygensis, and Martin Bradley. But I would also like to make special thanks to the team involved in this, specifically Peter Imris, who's been involved in Work Package 2 simulation, but also to probably the order of 20+ people from more than half a dozen different organisations who share their expertise. This project is aimed at raising the awareness of the risks associated with mass adoption of EV charging and vehicle to grid, and that covers a really broad range of stakeholders. The presentation today, some of the topics later on are focused specifically at grid operators and distribution companies. However, much of the learning from this will also impact regulatory activity and will have to be implemented potentially with changes to EV chargers, impacting charge point manufacturers and energy system companies and aggregators. And the findings here, some of the topics are very UK specific or GB grid specific. Equally, many of the factors apply globally across the world. And ultimately, that we see addressing some of these issues will have to be done over the years on a global basis through standardization activity. The issues that we are dealing with are all related to the challenge in the transition to net zero. Renewable generation has been a major change for electricity grids around the world. We're ending up with generation from renewable sources, which is intermittent and weather dependent. There are issues and challenges in terms of grid stability with reduced inertia and short circuit levels. And with the introduction of much more distributed generation within the distribution network, we're seeing voltage rises, which is historically have not been seen, as most of the power flow was from centralized generation down to consumers at distribution level. Another concern has been the impact of tripping of generators coincident with other faults on the network. Within this project, Project REV, we have been focusing on increases in demand and specifically from EVs. But again, many of the findings are also applicable to heating systems as heating becomes increasingly electrified. What we will highlight is a major increase in electricity demand, and more specifically, that we are getting a different type of demand. This is coming from smart systems, which are software controlled loads, and with vehicle to grid as well, the opportunity to provide power back to the grid. And this software controlled mechanisms gives us the opportunity to reduce the peaks of demand and vary demand much better to match the variable supply. However, this introduces some new system risks which have never been seen before. And the size and scale of adoption that we will see of this technology is going to occur very, very quickly. And that's what we want to highlight within this project. So Project REV has been aimed at identifying and communicating the risks to a broad range of stakeholders and forecasting potential issues that we might see in the 2030s or earlier. But generally what we're trying to do is take a vision not of what's happening over the next 2 or 3 years, but what's happening towards the end of this decade and into the 2030s, allowing potential time for mitigation actions, and that's across many different areas. The challenge of low carbon technologies within the electricity grid is that the GB electricity grid wasn't designed to support massive demand from individual consumers. So typically, the GB grid has been designed for something of the order of 2 kilowatts per household as a peak after diversity maximum demand. We've seen solar PV generation come along, and that has added power flows in reverse direction with houses producing net export. And V2G will further add to that as we see increasing adoption of that type of technology. On the demand side, EVs are increasing the demand that is seen per household, and heat pumps take that further. So we are seeing the potential for much, much higher demand than has ever been seen before in terms of peaks, and also much greater export from domestic users. To give an idea of the size and scale and pace of that, forecasts from National Grid ESO and their future energy scenarios show that in at least one of those scenarios, there is 100% increase in energy demand over a period of a year by 2035. And 2035, I used to say it was 15 years away. It's getting much closer. We're now down to only 13 years away. So this is a rate of increase in energy demand which has never been seen before within the GB grid. And this requires changes both in terms of generation, transmission and distribution networks, but also much greater use of flexibility services that can be provided by smart control systems. Within work package 1, we identified 6 ways in which electric vehicle chargers present a risk to grid security. And I would recommend anyone who hasn't taken a look at that report to read that, as well as looking at the work package 2 report, which we'll concentrate on today. But just as a quick highlight, those risks to grid security are lots of EVs turning on and off at exactly the same point in time. For example, when there's a cheap tariff at midnight. Some mitigation techniques taken to turn those step changes into in load into ramps, but again we may see potentially some very rapid ramps of increase or decrease in demand. There are challenges in terms of oscillations, with groups of chargers potentially switching on and off repeatedly. And within this work package, we've considered more details of impacts on degraded stability, and Martin will cover those later on. There are also challenges in terms of demand controls, the final mechanisms by which we help prevent system collapse. Again, we'll talk more about that. And system restoration, the challenges of turning power back onto the grid when in that very rare, highly unlikely situation, the whole of the country goes dark. How do we repower things? So those are the issues that we raised within work package 1. And within work package 2, we've touched upon a few of those in much more detail. And we'll go through and describe some of those. So within work package 2, we've been looking at the emerging risks and requirements as low carbon technologies grow. And first, we can consider the power domain. So the power domain, where we have PV, we have EV chargers, heat pumps, and potentially even home battery energy storage, and other smart appliances in the home, which are both consuming electricity, providing power back to the grid, and potentially providing services both to distribution companies and to transmission and system operator. In order to control these systems, we are looking at controlling a very large capacity. So EVs and domestic heat pumps are forecast to be up to a total capacity of 100 gigawatts by 2030. That is, if all of them were on and fully charging and fully heating at the same time. That's an enormous potential load compared to typical peak demands on the grid currently. If we can get this right and control the timing of those demands to fit availability of supply from renewable generation and avoid adding too much to peaks, there is a potential forecast saving of up to 400 million a year by 2030. So these smart devices are controlled by the digital domain. Each of the individual devices typically will be connected to a controller and out to the internet for control by aggregators and other organizations, or potentially control through the smart charging mechanism and the control system applied there, the smart BCC system within the UK. All of these devices in the digital domain have the capability of responding to control signals such as time of use tariffs, or as a dispatchable service, or a pre-programmed frequency response type service that is providing services to transmission and distribution operators. They are remotely controllable, so consumers also have the ability to directly turn things on and off when they want to. but also, sadly, this opens up the opportunity of control by hackers. And alongside this, all of the device manufacturers may also have mechanisms to provide services into these devices. Typically, that might not be direct control, but it could, for example, be software updates. This introduces a number of different operational risks. So how will these systems perform during power systems events? What are their fault ride-through characteristics? And we'll talk more about rock-off and voltage ride-through characteristics. What are the risks of consumer behavior causing lots of devices to turn on and off at the same time? So the concept of panic charging when there's a storm predicted. What's the risk of that? Market design, we have a market in the UK based around a half-hourly settlement period. This means a lot of tariffs align with that half-hourly interval and have the risk of many charges turning on and off at the same time. And overall, the complexity of the digital domain here leads to risks of many different types of interactions. In terms of the grid operator side of things, there are new capability requirements. How do we get data to plan and do post-fault analysis? What sort of analysis techniques do we need to look at the risks of coincident tripping? How can we schedule these resources and control them? And what are the digital contingencies that we may need to consider if any of these systems fail? And then if we have to go through a process of restoration, how will all of these smart loads behave? What is the risk that they all default to full power when they lose communication and we end up with massive cold load pickup? So looking at these in turn, we believe there's a need to develop a digital decarbonisation capabilities program, looking at the impact of on the system operator and distribution operator, the capabilities that they are going to need within their new systems and services. In terms of looking at the power domain, there is a need in terms of updating the regulatory framework, covering things such as fault ride-through requirements and what happens during restoration. The market design will need to evolve over time. How can we control these loads so they behave in a smooth manner? And security standards, SQSS, may need to be updated significantly to take into account the impact of the major new control systems that are coming in, controlling the 100 gigawatts of load that we talked about earlier on. And finally, the regulatory framework also needs to consider things like IT resilience. So the impact of cybersecurity across what is a really complex infrastructure of control systems. So moving on from those top level recommendations, we're going to go through and talk about Work Package 2 in a little more detail. We have selected just a few topics from this, going through under and over voltage, rock-off and vector shift, and stability analysis and load response. And I'll start by talking more about under and over voltage. So in electricity grids, voltage control response times at network level typically tend to be fairly slow. Voltage control is undertaken through mechanisms such as tap changers, which are electromechanical. They wear out, so there's targets to try and ensure that they don't operate too quickly, and there's coordinated operation between transmission and distribution. This means voltage excursions may occur for many minutes, and this is reflected within the statutory voltage limits and measurement techniques used within the GB grid. So we may think of our 230 volts plus 10% minus 6% as what voltage we'll see for a typical consumer. That specification is actually based on a 10-minute average, and it is possible to end up with excursions beyond that for quite significant periods of time. Sample data from some PV has shown that 29% of sites were over plus 10% of the nominal voltage specification within just a 3-week monitoring period. So it's not that voltage excursions outside what we think of as the normal limits for short periods of time are uncommon. And the thing to realise is that electric vehicle chargers and vehicle to grid systems are sensitive to voltage excursions. Specifically, EV chargers in some respects are a new class of load where they include both under voltage protection and over voltage protection. And they can be fast responding. So typical response times to under and over voltage conditions, depending on the scale and size of those excursions, can be within a matter of seconds. And that is well within the limits which are allowed within the quality standard SQSS. And this gives a risk of potential cascade. So specifically, if we consider an overvoltage condition, if there's a small overvoltage condition in one area and we start to lose load in that area, that load is tripping, there is then a risk that voltage goes up further and we have a cascade situation. And within the GB grid, there's also some thoughts of expanding the voltage regulatory range in terms of the lower limit, changing that from -6% to -10%. That's aimed at trying to give the DNOs greater flexibility in terms of dealing with the voltage drops that come from increasing loads. But the regulatory limits associated with tripping thresholds have very much been based around the current limits for voltage regulation. So there's some challenges there that we go into much more detail within the Work Package 2 report. If we consider the effect of voltage excursions, within Work Package 2, we took one casual example, one specific example, which was looking at evening peak in 2035, potentially where we have 10 gigawatts of generation coming from vehicle to grid. And we looked at a real life situation of a 3-phase fault on a 400 kV part of the network in a relatively rural location, actually quite close to our office. That fault was cleared within 80 milliseconds, so typical fault clearing time. But from the estimates of the current performance of grid-connected inverters, we would anticipate that during an incident of that type, we might see up to 250 megawatts of generation trip. So 250 megawatts of V to G. And that's considering that particular use case in a rural location, or the particular example in a rural location here. If we looked at a city and considered a major 3-phase fault in the centre of London, potentially we might end up with much higher levels of coincidence loss. And this is a concern in terms of the way in which the ride-through performance for grid-connected devices is defined, both in terms of load and generation. And within the report, we highlight some great work that has been done within Australia, looking at PV inverters, highlighting that quite significant proportions of inverters end up disconnecting, even for relatively short and relatively small voltage sags. And part of the issue here is that those voltage sags may combine both a voltage change and a phase change at the same time. And Martin will talk much more about this later on. So within the section looking at under and over voltage, we are making some specific recommendations. So firstly is to recognise and actively manage the risks with mass coincidence tripping due to under and over voltage being experienced by low carbon technologies. And specifically, under and over voltage tripping has been considered in detail with regard to generation in the past. What we would highly emphasize from this project is that we will see similar effects from loads going forward. So power converter connected technologies generally will include under and over voltage protection, and the fault ride-through requirements for those is not clearly defined in an explicit manner that has great consideration for the 100 gigawatts of load that may be appearing and the risk of ending up with coincidence tripping of load. We also highlight the risks to grid stability from coincidence tripping needs to be considered as part of any changes to voltage limits in the GB grid, and specifically the consideration of change from -6% to the -10% limit, but more generally also within things such as the voltage control processes used both at transmission and at distribution level. And finally, what we would highlight is that improving time resolution of low voltage grid monitoring is an important aspect. We have struggled to find any data, any substantial data source which provides good voltage resolution down to and time resolution of voltages on the LV grid, looking at the response time for EV chargers. So being able to detect under and over voltages which are of the timescale of a second to a few seconds. And increasingly, as we end up with more devices connected to the LV network with under and over voltage protection operating within a matter of seconds, it's important that we recognize that there is a need for data gathering right the way from transmission level down to distribution and LV network. So that brings me through the first section looking at under and over voltage and the work that was undertaken within Work Package 2 to investigate that. At this point, I'd like to hand over to my colleague, Martin Bradley.
Thank you, Andrew. My name is Martin Bradley. I spent about 30 years of my career with the National Grid Electricity System Operator and have been working with Sygenesis for just over a year now. So within this project, one of the things we looked at was the area of rock-off. So we know that vehicle-to-grid and other embedded generation will have rock-off protection. And we also know that sometimes these relays don't trip when you expect. So we wanted to explore what was the risk of potential cascade tripping due to unexpected operation of rock-off relays. Now we know that regulations define a threshold for rock-off tripping based on a pure sine wave, but we do know also that waveforms may be distorted, so that filtering is required within the relays. And the behavior, therefore, of the relay depends on the specific algorithm being used by the vendor, and these do vary between vendors. So the chart on the right comes from a project actually that Peter and I did at Brunel University a little while ago, and it shows the behavior of one vendor's relay with different levels of filtering. And you can see that the response of the relay will depend on the level of filtering that's applied. And this will also vary between different vendors. So we looked at a full GB network, and we used a built-in existing loss of mains protection relay within Power Factory and simulated what cascade tripping might look like. Rather than try and reduce the inertia of the network to 2035 levels, we simply set down the level of rock-off tripping until the first relay operated. And these results are counterintuitive, with tripping occurring first at remote locations. So the case we looked at was for the trip of an HVDC interconnector in the southeast. And what we found was the first site to trip was up here, and the next site a bit further up, the third site where it was in the top of Scotland, and then the tripping moved further down south. So actually this also reflects something that Peter and I found on a small network representation of the National Grid network on the project at Brunel University. The reason for this is that when you have a trip in the southeast, that excites a north-south oscillation. Although it's a DAMS, the half period of that oscillation is longer than 500 milliseconds. So in fact, it's longer than the rock-off detection time. So it actually effectively magnifies or exaggerates the rock-off on the whole network. So rock-off was increased, particularly in the north. And so the message from this is that the kind of national average level of rock-off shouldn't be allowed to approach the overall tripping level of 1 Hertz per second, because some relays will trip sooner than that. Another area we considered, and this is that's just a bit of a kind of request to National Grid ESO. So they are publishing some really helpful data on system incidents as part of the GC 105 and 151 provisions. However, this only includes a single national figure for frequency at 1 second resolution. And this does limit its usefulness, especially when you're looking at rock-off phenomena. So higher resolution frequency data from multiple locations would be more helpful. And in addition to that, publishing waveform data from system incidents would help with the analysis of complex disturbances. Particularly now we're trying to look at under-node voltage tripping, vector shift behavior, which we'll consider next, and rock-off effects. So the next area we looked at was vector shift impact on inverter-based resources. So inverter-based generators use a phase-locked loop to track the power system phase angle, so that the intended real and reactive power can be injected into the system. So from the inverter side, they have to know what the power system phase is, so they can set their own phase to inject the right amount of real and reactive power. So these phase-locked loops are designed to maintain their lock under disturbed conditions, so they'll continue to track the power system phase under some level of disturbance. But this capability can vary widely. Unlock can occur for vector shifts or phase jumps between 15 degrees in some cases, up to 90 degrees. Internationally, regulations are being introduced to specify right-through capabilities for vector shift events. And this phase-locked loop unlock has been is a well-known mechanism, well-known issue with inverter-based resources. This table here comes from an analysis in the US of an incident in Texas last year, where over 1,000 megawatts of embedded generation tripped. And the largest single cause, which is about 35% of that, was due to phase-locked loops unlocking, actually losing synchronism with the main grid. So this is an established issue. Coming closer to home, so we said a sudden shift in phase can trip generation either by phase-locked loop unlock or also spurious frequency calculations. So these embedded generators also have high and low frequency protection, and the calculation they use to measure frequency can be fooled by phase jumps. So that can also trigger unexpected tripping. And at the moment, the GB regulations for this embedded generation don't specify any requirements for vector shift ride-through. Actually, in the type tests, a test for phase shift is included, but there's no requirement in the regulations to meet that test result. EV chargers and other smart loads also rely on phase lock loops, so they will also be vulnerable to vector shift tripping. And the lack of any ride-through requirement does feel like a critical gap in GB regulations. This map here shows the vector shift around the southwest part of the GB grid for a three-phase fault in the southwest here. So locally, you have phase jumps of almost 60 degrees, and as these propagate around the network, they reduce, but they can still be fairly substantial, 25-degree phase shift at this point here. So recommendations in this area for rock-off and vector shift. First of all, the system operator needs to allow for a margin for regional variations in rock-off, rather than just assuming that they can work all the way up to the rock-off tripping threshold. Vector shift ride-through, we believe, should be specified in the regulations, for example, by grid code mod 0155. And we think it would be helpful to improve monitoring of rock-off and vector shift and sharing data beyond the current provisions, which are already very helpful in 105 and 151. So the third area of detail we looked at in this work package 2 was stability analysis and load response. So the mass adoption of electric vehicles and other low carbon technologies may impact system stability because their inherent load response to voltage variations is different to traditional load types. So we're not talking here about intentional demand side response. This is just the behavior of the load with voltage. And we're all familiar with the behavior of traditional loads, so resistive heating, tungsten lighting, induction motors, things like that. But these loads will behave differently, and there will be a lot of them in the future. Now, ESO needs to maintain three types of system stability: voltage, transient, and oscillatory. We'll consider each of those. And we carried out some very preliminary studies in each of those areas to test the impact of constant power loads. And this quotation on the right here is from a US document on the Department of Energy website. And it says, bulk power transmission system planning requires accurate models of all three components: generation, transmission, and load. But historically, most of the focus has been on generation transmission, and effectively load modeling has taken a bit of a backseat. So in GB studies, the Security and Quality of Supply Standard, the SQSS, requires that voltage step change limits must take load response into account. And this is a graph from the present sort of load models that are still in use. And yes, it does come from the days when we drew graphs by hand. When load models are required, ESO uses the most cautious of this legacy suite of models, one called heavy industrial, which produces the most pessimistic results. In time-domain simulation studies, constant impedance load models are used for these, both the transient and oscillatory studies, and that's in line with common industry practice. It's much easier algorithmically to study time-domain simulation with constant impedance loads. But we do recommend that these models for all three types, voltage, transient, and oscillatory stability, should be updated to represent present and then future load types. And also critically to include tripping functions where appropriate. One of the big features of these future loads will be, they will be active loads with their own protection, and that's something we've never had in the past. So looking at the voltage stability margin, ESO helped us with a study case modifying it to produce a severe voltage test case. We then applied varying amounts of constant power load, with the rest of the load being constant impedance. And as anticipated, the post-fault voltage steps increased as a proportion of constant power load increased. And we were looking at voltage steps down, but voltage steps up would also increase with higher percentage of constant power loads. So this may affect SQSS compliance, and then also the risk of smart loads tripping on either under or over voltage protection. But the lack of data on the present day characteristic loads means it's hard to say by how much that risk will be increased in the future. The second area we looked at was transient stability. And this is the ability of a power system to maintain synchronism after an event so that all the generators stay in step with each other. Again, ESO very helpfully gave us a double circuit fault case with a trip event in Scotland. And we increased export across this boundary until the system was just unstable. And this is the base case shown on the graph on the right here. And then we converted some of the load from constant impedance to constant power. And what we found unexpectedly was this helped the system become more stable. To be honest, we were expecting the opposite, but it actually improved system stability slightly. As you can see from these two other curves on the right here, with 10% and 20% of constant power in the study. So this suggests that actually revising load models could give some modest increase in power transfer across boundaries that are limited by stability issues. The third area we looked at was oscillatory stability, and this is the ability of the power system to maintain adequate damping with or without an event. Again, we used a double circuit fault and trip in Scotland with data supplied by ESO and increased export across this boundary until we had poor damping post-fault. And this is the base case curve here, the dark blue line. Then, as before, we converted 10% or 15% in this case, to 30% of the load to constant power. And again, unexpectedly, we found that the damping actually increased, damping improved on the system. So again, in cases where oscillatory stability is the limiting factor, there may be some modest improvement of power transfer possible by including some constant power load models in the network. So new modelling needs. So distributed energy resources and smart loads will play a significant active role in balancing supply and demand. As I mentioned earlier, these do include protection systems, which can impact system-wide performance during contingency events. So the traditional approach to system modelling has treated transmission and distribution as largely decoupled systems with very simple and highly aggregated load models, effectively treating load as passive or kind of dumb loads. And these models are unlikely to give reliable results with a mass adoption of active consumer loads. And in regions of the world where there have been major DER contributions to incidents, there have been significant moves to enhance DER modelling, both in terms of the models and the analysis tools themselves. So, for example, in Australia, AEMO have undertaken this multi-year programme of work to understand the aggregated behaviour of distributed energy resources during and following power system disturbances. So the next area we looked at was electromagnetic transient models. Now, ESO is already exploring the use of electromagnetic transient studies through the TOTEM Innovation Project, which is highlighted on the right. This is to address modelling challenges related to large-scale inverter-based resources. But with vehicle-to-grid forecasts to provide up to 25% of generation at times, these modelling challenges will also extend to distribution-level resources as well. For example, the possibility of new types of control system interaction. EMT studies, for example, as envisaged in the TOTEM project, would enable detailed performance characteristics of EV chargers and vehicle-to-grid to be analysed and appropriately represented in transmission studies. So within TOTEM, part of the description of the project says conventional phaser-based RMS simulation tools have limitations in studying weak low inertia systems due to the level of detail that's represented. And really EMT-based models and simulation are needed to de-risk the integration of new technologies considered above. Demand control was another area we looked at. So in the existing grid code, section OC6 provides the system operator with two mechanisms to manage a shortfall in supply if, for example, there's insufficient generation forecast to meet demand. So the first of these is demand reduction, delivered in part by voltage reduction on the distribution networks, which is implemented by the distribution network operators. And secondly, low frequency demand disconnection, where relays out in substations progressively disconnect blocks of demand as the frequency falls. With constant power smart loads, voltage reduction will have no effect on their demand, although it's possible that some devices may trip on under voltage protection. And secondly, operation of low frequency demand disconnection will disconnect vehicle to grid generation and other embedded generation along with demand, which will reduce its effectiveness. Specifically, battery energy storage systems are likely to be generating if the frequency has fallen, and these would also be disconnected from the distribution network. So studying the effectiveness of OC6 measures in the medium term will require representative modelling of smart loads, including voltage and frequency response, and control and protection behaviour. So the chart on the right comes from a Fraser-Nash report for BEIS, talking about the effectiveness of demand disconnection. And basically, if you have demand disconnection, load shedding, as it's described here, then outages tend to be shorter and affecting the smaller numbers of consumers. Without any load shedding capability, then outages tend to be longer and affect larger parts of the network. Then we consider the case of restoration, as Andrew mentioned earlier. Now, there's been a big project running by ESO called the Distributed Restart Power Engineering Trials, and this is in collaboration with other network operators and transmission owners. And some of the published results from this study show that when energizing network from the LV side for the first time, you can get overvoltage excursions of up to 71% during transformer energization, and with total harmonic distortion up to 78%. So these are very high levels of distortion. So significant frequency and rock-off excursions can also be expected. And this graph on the right is taken from the simulated results of a smart zone controller looking at distributed restart. And again, you can see very large frequency and rock-off excursions. So there's a real risk that EV chargers and heat pumps will trip on overvoltage or unlock phase lock loops during restoration because of these highly disturbed conditions. And tripping of large tranches of load disrupts the frequency balance in an island and potentially cause that island to collapse. So this is an area which I think is a potentially significant concern in the future, is how these load islands will behave during restoration. So V2G and other forms of battery energy storage system have the potential to offer significant benefits to the restoration process, as long as their control systems are designed with restoration conditions in mind. But there are significant potential downsides I've just mentioned. Data on the location and characteristics of these devices may be limited. At the moment, there's no requirement, for example, for V2G data to be provided to network operators. And while some devices may be available immediately on restoration, others may have a delayed return or require manual intervention. And communication channels may also be disrupted because internet communications may rely on a number of different sites around the country, and those sites may be restored at different times. So communications to smart devices may take time to be restored. And also, Andrew touched on the issue of cold load pickup earlier. This is likely to be significantly higher and of longer duration than traditionally been expected. So EV chargers may operate at full power as vehicles made up for lost charge, and consumers seek to protect against further losses of power. So if there's been one blackout, consumers may be concerned that another one may follow. So they may all try to charge their vehicles to the full amount. And heat pumps may run continuously at full power, potentially with sort of manual override boost as well, if the power's been off for several hours and houses have gone cold, to help recover those house temperatures back to normal. So these are much higher intensity energy loads than we've had in the past. So the cold load pickup could be significantly higher and of longer duration during restoration. So to summarise just some of the issues I've touched on in this section, so our recommendation is that ESO should be developing enhanced load models to improve the accuracy of stability simulations, which recognise significant change in load behaviour. Investigate how best to include the impact of protection systems on low carbon technologies in stability studies, and also actually in the restoration studies I mentioned just now. Assess the potential impact of smart system controlled low carbon technologies on the OC6 demand control measures and cold load pickup, and develop measures to mitigate these risks. And also look for ways in which we can exploit the capabilities of EV chargers, vehicle to grid, and other low carbon technologies and how they can enhance voltage control. So on that note, I'll turn back to Andrew.
Okay, well, thanks very much, Martin, for that. And I would just say, if anyone does have any questions, please do feel free to use the Q&A button and put some questions in there, and we'll try and get to those at the end. So I'm going to try and summarize feelings on this project as a whole now, and would like to start by saying mass adoption of EV charging and other low carbon technologies is coming very soon. One of the things that we haven't touched upon on the presentation so far has been the energy crisis, the dramatic change in terms of the relative price of all types of fuel. And one of the concerns is that some of these changes, particularly in terms of the adoption of smart tariffs, time of use, people trying to find ways of minimizing their bills by choosing the timing of their loads on grid, could have a significant impact earlier than we expected if we see mass adoption there over the next 2 or 3 years. But going towards the 2030, we expect to see 100 gigawatts of smart connected devices. This is smart charging, smart heat pumps, and so on. And to bear in mind that 100 gigawatts of devices is well in excess of the current peak demand. And all of these are going to be controlled by smart control systems. Those Internet of Things systems, which are obviously give great flexibility to users, great ability for remote control, but have issues in terms of potential new failure modes. And we have to bear in mind that smart charging is in its infancy. We're very much at the days of equivalent to the 1G mobile phones, very, very early in this technology. We will see dramatic changes over the next few years. It is important to realise that we need to prepare now for the 2030s in terms of the system design, the way in which we're going to manage the balance between supply and demand, the way in which we are going to manage through contingency events, failures within the system, cyber attack. Key within that, sadly, in some respects, are regulations. In many respects, nobody really likes to be operating within a highly regulated industry, but without those regulations, we couldn't manage to keep the lights on and keep a stable system. And regulatory action in this area will occur on a regular basis. We've seen some great activity going on through some of the smart charge point regulations coming out of BEIS. We've seen updates to G99 through the Energy Networks Association. There's the activity with BSI on energy smart appliances. There's going to be a really broad range of regulations which are needed to ensure that we have a smart, secure, and efficient and cost-effective system going forward. And part of those regulations will flow through into standardization, looking at greater opportunities for interoperability between systems. And around all of this, the market's design itself will need to change. It will evolve over time. And there are some significant challenges in terms of updating all of these areas and to meet the challenge of a decarbonised grid in the 2030s, where we are balancing that grid on occasions by varying demand to meet supply. And one of the key issues in all of this is that we need to balance the requirement to maintain system operability and security, while at the same time allowing very, very rapid innovation. And we definitely don't have answers for all of that. There are many organisations who will push back against any further regulation and standardisation activity. There's others who see that it's essential. But overall within this, anticipate a great deal of change over the next 8 years to the time we get to the 2030s. So just to go back to the activity within Work Package 1, I would highlight that in the report there is a vast amount of detail that covers a really wide range of potential failure mechanisms. So this summary slide shows 6 general classes. Within the report, there are probably 100 or more individual potential issues which have been highlighted. And anyone who has a real interest in this area, I would suggest go back, read it in detail, read it again. There is a lot within that. And that has been recognised. We've had a great deal of interest from organisations all around the world from the findings of Work Package 1, because it brings together a really holistic view of the potential threats to system security, which come from mass EV charging, vehicle to grid, and other smart systems in general. Moving on to Work Package 2. Work Package 2, the detail, we've gone into significant detail in particular areas. I would highlight the part on the right-hand side here, saying that there are potential benefits. So this whole presentation could have come across as being incredibly negative about EV charging, vehicle to grid, smart charging. The thing to realise is that there's potential to save hundreds of millions, if not into the billions, by being able to have effective, reliable, resilient smart charging control systems. And even more through smart control of other devices in general. So our recommendations are very much to look at decarbonisation capabilities programme, look at the regulatory framework in the power domain. So this is looking at things like the fault ride-through and vector shift ride-through that Martin was mentioning earlier on. Look at the reforms required within market design. And we strongly highlight in a number of different points the challenge of the market in the UK being based at around a half-hourly settlement period. That tends to promote steps every half hour, and that is a real challenge to manage. And there may be need for reform of the market in that area. There will be need for other forms of mitigation against load steps occurring every half hour. We will also try to draw attention to the security and quality of supply standards and suggest introduction of the consideration of digital contingencies, not within the central control mechanisms normally considered within the transmission and distribution systems, but the digital contingencies related to smart charging control and aggregation in general. It won't be very long before aggregators have multi-gigawatts of demand and small-scale generation under their control, and that presents new threats in terms of the impact that it could have on system security. And within all of this, we would highlight the complexity of the digital domain which is being introduced. We are introducing quite complex IT systems which depend on web services, internet service providers, mobile phone providers, with multiple different organizations involved with this, from the vehicle manufacturers to the charge point manufacturers. This presents a very wide attack surface for cybersecurity threats and introduces wide-scale dependencies on third-party tools. And again, having a good understanding of that will make an enormous difference in terms of the reliability and system security that can be achieved. Putting a more positive note on this, I bring back the analogy to mobile phones. If we are now at the 1G technology for smart charging, what will 5G look like, or 6G, that we might expect at the end of this decade or into the mid-2030s? So Julie and Leslie from National Grid highlighted that by the end of this decade, we won't be dispatching generation to meet demand, as we've done for the last 100 years or more. We'll be dispatching demand to meet generation. And this is being able to use the flexibility of demand-side response to match the varying timing of generation that comes from renewable sources, such as solar and wind and tidal. So that ability to control demand and control the timing of demand to better match generation has an amazing capability in terms of being able to reduce system operating costs, reduce the need for curtailment of wind generation, for example. And looking specifically at EV charging, we see that current EV charging control systems are again at the 1G or the 2G level. Going forward, we anticipate that smart charging control will be pervasive on every device. We anticipate that all of the issues that we have identified earlier on will be addressed, and will be addressed in such a way that we have dependable, resilient operation that behaves in a sensible manner, not just during normal operation, but also during events such as restoration, major communication systems failures. The type of issues that we have identified can all be addressed, and relatively easily from a technical standpoint. The challenge in many cases is getting agreement in terms of what is required and what is best for grid operations, and what is also good for consumers, and then looking at the required regulatory processes to mandate these requirements. More generally, we see that it is likely that a very large number of vehicles will end up with vehicle-to-grid capability and vehicle-to-home capability. So being able to provide quite complex services to the grid, not just being able to time the demand to fit available supply, but also being able to provide grid forming controls, so the ability to provide virtual inertia, be able to provide reactive power, the type of things that you would normally only anticipate to be seen from large grid scale assets, and even those, its own grid forming is only due to be appearing in the GB grid over the next few years. But by the 2030s, we see that this is likely to be very common within EV systems. And part of this relates to the ability to provide vehicle to home and provide backup power to your home if there were a power outage, or vehicle to load, the ability to plug that power tool into your car or your pickup truck when you're away from home. So there will be much greater facilities available within EV charging control systems than has been seen in the past. And this is looking out to the 2030s. So we are anticipating that distribution companies in future may be able to encourage the operation of safe grid islands to improve system resilience. So if you're in a remote community with long overhead cables which are subject to damage by storm, wouldn't it be great if that local community, the village or town, was able to operate as a grid island, making use of the embedded distributed generation from solar, PV, wind, and alongside that, be able to use the storage capacity within vehicles to help provide short-term balancing services, voltage control, and inertia type services within that grid island. So going forward from here, the project has raised a really broad range of issues. We are actively involved in trying to address those, some through grid code activity. We are in discussion with BEIS, ENA, IET regarding many aspects of regulation. But the key objective for this project was to raise broader industry awareness and seek further involvement across many of the areas that we've discussed today. And that includes EV manufacturers and charge point manufacturers, the energy system companies, aggregators, and distribution companies. And overall, our vision is that there is a potential for incredible capability of bidirectional power flow from electric vehicles and more generally other battery energy storage systems to totally revolutionize the way in which we balance the electricity supply, helping match supply and demand, and being able to do that both in terms of public grids and local microgrids. And some of those local microgrids may include grid islands, including part of the DNO infrastructure. And finally, I'd like to say thank you. Thanks to the team within Sygensis. Thanks to all of the active contribution that's come from National Grid, ESO, and especially for the funding, obviously. We had great input from a broad range of collaborators from the Energy Systems Catapult, UK Power Networks, EPRI in the States, National Physical Laboratory, and the strength of the report and the work that we've done has been based on numerous earlier research by numerous authors, and we are really grateful for that. And thanks to all of those who have shared their expertise. We're really keen to collaborate going forward. There's an email address to get in touch with us. But now what I'd like to do is hand over to some questions. We have